Eagle strike, ladies and gentlemen. Team 114, first robot. Let me get Homer off the table here.
All right.
Ben, Mina.
Welcome to the first robotics competition and the 2016 Tournament Challenge First Stronghold. The Alliance quest is to breach the opponent's defenses, known as the Outer Works, weaken their tower with boulders, and capture it. The low bar in position 1 is permanent. The defense in position 3 changes periodically by audience selection. Opponents are savvy and will be strategically selecting the remaining 3 defenses to strengthen their outer works while in line for the next match. There are more than 10,000 possible field configurations. Robots start in the neutral zone and may have one boulder each.
Good? Alright.
Line for the next match. There are more than 10,000 possible field configurations. Robots start in the neutral zone and may have one boulder each. Additional boulders will be placed on the midline and in each castle. Alliances may assign a spy bot to start in their opponent's courtyard and a human player to occupy the spy station to signal intelligence about activities on the far side of the field to their castle. The first 15 seconds of the match, the robots are autonomous and may earn points by reaching their opponent's outer works, crossing defenses, and scoring boulders in goals. During the following 2-minute and 15-second teleoperated period, human drivers remotely control their robots. They retrieve boulders, overcome opponent defenses, and score boulders and goals from their opponent's courtyard. The first time a robot fully crosses a defense, some of the base lights will turn off, indicating that defense's strength is reduced. On the second crossing, all lights turn off, indicating that defense is considered damaged. Once any 4 of the 5 opponent defenses are considered damaged, the outer works are breached and the alliance receives points. Human players deliver boulders to their secret passage through their castle wall. Alliances may have only 1 robot at a time in their own courtyard to defend their castle. As boulders are scored, the tower loses strength. Once enough boulders are scored in the opponent's tower, the opponent's flag will drop, indicating the tower has been weakened and can now be captured at the end of the match by surrounding it. During the last 20 seconds, robots may extend to reach the tower rungs and scale the tower for additional points. If an alliance captures their opponent's tower at the end of the match, their flag is raised and the alliance earns more points. The alliance with the highest score at the end of the match earns the win. Step into your castle, proudly raise your team's standard, and face the challenge ahead of this year's first robotics competition, First Stronghold.
Hello? Okay. So, let me preface all this. We are from Los Altos High School. We're part of First Robotics, which is who made that big video competition. Essentially, they do a yearly robotics challenge. They have different levels, Lego level, FTC, which is like middle school and high school level. We're part of the high school level. To boil it down, every year, every January, the first week, we will receive a game video like you guys just saw. And at that point, we have 6 weeks then to build this fully fledged, pretty large robot, which will then go on to compete against, about 30 other teams at an event, and continue up it, kind of exactly like a sports playoff, right? So this year's game, which you guys saw, was called Stronghold, and it essentially boils down to 3 major components, which is the autonomous period, the teleop period, and the end game. So the autonomous period was described there, but I'll repeat it quickly. Robots had to start behind the line, and you could do practically anything that you can do normally just for bonus points. In this case, our robot could cross one of those defenses and could cross any of the defenses shown and gain us just those points, as well as make sure that we don't need to do that later on in the match. And then during the teleop period, it's when drivers take control. I actually drove this robot during competition, so that's when I would step up to the plate and I would drive it around. And at that point, you're against other robots on the field. They're trying to defend you. They're trying to also score points on your side. And during tail light, what you really want to do is score those boulders, as they're called, their standard dodgeball size, into those about 7.5 feet tall goals. And that is relatively tough, given the size that the goal is relative to the size of the overall dodgeball. And then again, in the end game, just you drove up and made sure you were in the right spot, and you got more points. But I will, if you guys want, demo the robot that we have here. This was, I wish I could take all the credit, but there was about, we have a full team of about 30 people. I'd say we had 10 people working on this every night until at least 8 o'clock, Saturday to Sunday. That works, right? Whole week, yeah. So we practically live at the robotics shop when we go through and build this thing, and we do manage to do it all in 6 weeks, which I find very surprising. This particular robot that you see in front of you, it can do everything that was mentioned in the game video, except for do that hanging at the end. Looks like we've got some GoPro footage playing right here. Yeah, I'll see if I can, there we go. So you can see right there, we're crossing get out of the way. We're crossing what are called the defenses. Right there is what's called the moats, the little separation with those 1 inch tall gaps on both sides, or towers. That looks like might not do it, but that was the portcullis, essentially teeter-totter, so you had to level to your side and cross over. The one going over there is the ramparts, super easy, just make sure you can drive over it. And right next to it is what's called the low bar. That was probably the hardest one for this game because it meant that your robot couldn't be taller than about 14 inches to go through it.
Which competition was this?
This was at TC Champs, the off-season competition. And the other thing you see there is the rock wall, but also mentioned in the video were the portcullis, which is the one we lift up to go under, and the sally port, which is what opens towards you like a door. We were fairly successful, I would say, or I'd like to think, especially at the video shown right here, which is when we had a little bit of extra time to go through and wrap up the robot. After that 6 week period is up, we have to put the robot in a giant, essentially, Ziploc bag and can't touch it until you compete with it. So having a little bit of extra time just to tune in the code and all that, it's really nice. But I'll let this continue playing, and I'll just go through and kind of walk over some of the systems of the robot quickly. And then we'll make it move around and that kind of stuff.
Briefly, one question.
Yeah.
Was your technique to be at a given specific distance and a specific angle to the target, and then always use constant energy?
No, and I'll go over that later. We actually had a computer vision coprocessor. I was going to go over quickly the more mechanical aspects and then go into a bit more of a complex. The robot itself was constrained by size limits given by FIRST. In the current configuration, it meets all those size limits that you can then extend out of. So in the frontier, we have what we call our flippers or tomahawks, depending on who you ask in our team. These actually managed to accomplish 2 of the harder defenses. The portcullis, which we would just ram straight into and essentially just use the wedge of it to lift it up and over our robot. We had a hard rail going over the whole top so it wouldn't snag on anything. As well as these allowed us to bring down the portcullis onto our side so we could drive up and over. I'm not sure if that was shown in the video or not. And then on our intake in the back here was to grab balls off the ground since we cannot feed them directly into the shooter. And both of these mechanisms pivot on a pneumatic hinge. This one right here, the intake, has what's sometimes referred to as a beaver tail, which is, it uses polycord, which is very flexible, very resilient to changes in angle, which we did in a figure-8 pattern, which allows us to only have one motor driving that to center the ball, and then another one to bring it actually into the shooter. Our shooter itself, in the middle of the robot, we actually had to design stuff around that just to make it fit. It's acting off of 2 different flywheels, which of course spin up, and then we have a pneumatic cam kicker to kick that into the flywheels and allow it to actually shoot out. And that shooter itself can rotate roughly 170 degrees to go from the intake all the way over and shoot into the goal. Reason being that we didn't want to, we wanted to minimize the amount of times we had to turn around during a match since you only have that fixed amount of teleop time. Besides that, we had to fit all of the electronics in a tiny box the size of a shoebox. I'm not so happy that we had to do that, but I'm happy that it worked. Many hours went into that. Inside the electronics, and this will cover some more of the complexity, we have an NI Rio, which is an ARM-based system from National Instruments, which is running Linux with some coding libraries at this point, which is provided to us from FIRST, and then you expand off of them. We have the co-processor of a NVIDIA Jetson, the TK1 developer platform, which is loaded with CUDA cores, so based off that we were able to do really nice vision tracking of the target, and from that vision tracking calculate the angle to the target both in X and Y, as well as the distance to the target just using trig, and then send that back to the main controller. And we could have used kinematics, but we found it was much easier just to do a simple lookup table, since we only had a few different positions in which we really needed to change the angle of our shooter, because we made it pretty overpowered for what it needed to do. So based off that, our robot would rotate to the angle. I had one button I would press for this sequence to happen. Rotate to the angles that was lined up with the target. That's based off of a PID loop. And then rotate the shooter, another PID loop, to the specified angle based off the lookup table. Spin up the motors, and of course shoot it with the pneumatic. And I would say we made about 9 out of 10 shots, and that 10th shot that missed was typically because I screwed up somewhere. Or him. David over there, he controlled the Xbox controller on here, which did more of the robot subsystems. So he would control the rotation of the two different mechanisms at the top, and some of the rotating of the shooter. And I guess now is probably a good time to drive it around a little bit and just go over what it could do while you're able to see. David, you know my only microphone. You can speak if you want. Or I'm sure you guys can hear me from here, probably. All right, I'll kind of shout at you. I'm kind of used to that. So we have on the robot a 6-wheel drivetrain, 3 on each side, with a drop center, which allows us to rotate very cleanly. That is, the middle is dropped by about, I think we did about ½ an inch on the middle wheel. So that it pivots on those two as opposed to trying to actually pivot on all of them.
Are you using TZ drive?
No, we're not. So what we have is the manual control. We were driving tank drive, which is 1 joystick for each side. Forward backwards controls the specific forward backwards of that side of the robot, which allows you to do some very fun things such as just spinning the dime, driving backwards, driving while turning. A lot which can't just be accomplished with just the standard arcade drive, which is forward, backwards, left, right, all on 1 joystick. David, if you don't mind bringing down the 2 mechanisms. The pressure's kicking in there. I might need to speak a little louder for that. It's fine, don't worry. The reason we had to have those go down is not only so that we could actually use them during the match and use them for the designated purpose, but like I said earlier, to fit within the size constraints, as well as to make us more offensive to avoid defense from the robots.
That's the compressor, right?
Yeah, that is the compressor kicking in there. We do have a small leak somewhere that we never bothered to fix since it's a 2-minute match. Hopefully she'll finish. There we go. And again, during the match, we'd have David doing the actuation of those 2, and for each different defense, we'd have a different configuration of the robot. Either one was up, one was down, both were down, or both were up. For instance, I would line up on the portcullis, which is that little teeter-totter one, and signal when, and he would raise them down. He would flip them down, bring them to our side, flip them up, and we drive over. And the intake, he also has control of. That's that beaver tail at work, which could centrally ball as well as then draw it in, or if we got stuck on something, hopefully push it out. If you don't mind rotating the shooter, do you still have control of that?
Yeah, I can only bring it down.
All right.
No, I can bring
there
it
we go. So it does rotate about 120. We're not going to the full rotation because we need to, as well as we'll probably miss because it would hit something. The little LED ring on the front, the green LED circle there, that is to track the target. The target was I guess the goal in this case, was surrounded by a U-shaped retroreflective tape, which, if you guys know what that is, essentially allows light to bounce back at the same angle that it was hit. Which means only from the camera you can see the target as green based off the LEDs and everything else as normal. And from there we will do in this case, an HSV threshold on it and recognize it using contours to make sure that it was indeed the target that we were tracking and not just someone's shirt, something like that. And like I said, off that, do actually an azimuth calculation using those old little devices to navigate on seas to get the angles that we needed in both X and Y. And simple trig, since the target is at a fixed height, able to get a distance. I would demo that, but it was hard enough getting this in the back of my car, let alone a 7-foot tall tower.
So you used OpenCV?
We did, yeah. So the NVIDIA Jetson is a full-on Linux system. In this case, we have it run a simple startup script, and it's running OpenCV in C++, and setting that back through a thing called network tables, which I believe is mainly first used. Essentially a real-time socket connection between the two.
How well did you guys do in the contest?
We did really well, actually. I'm really happy about this, especially if you saw Robot last year. This year, I don't remember specifically what place we placed in. I think we were always top 8.
We hit, I think, 7th last, but we hit top
probably
4 at one point.
Yeah, so
Which competitions were you in?
we competed at SVR and at Davis or Sacramento, whatever it's called. And then off-season, just GC Champs, and we will be at Madtown Throwdown.
So I was curious, did you get any technical awards?
Not this year.
Because, I don't know, your targeting should have gotten some.
Well, we're up against 254 and 971.
Did you talk it up?
Oh yeah, no, I talked it up like crazy. I wrote that thing, late nights, fueled by coffee. So it's my baby right there, the vision tracking. So I bragged about it every chance I got, as you might be able to tell.
I'm surprised you didn't get at least.
Well, 971 got one of them at one, and 254 got one and another for the vision tracking on a phone, which was connected to it. Was there a question? Yeah?
Yeah, so how much are high school students expected to be able to know, to be able to do? And how much construction do you have to do, original construction?
Yeah, so this is actually all CAD'd ourselves, and most of it is hand milled in a 3-axis mill that we have in essentially what is a broom closet. We were lucky enough to have access to Tech Shop in San Francisco through one of the parents of a student who gave us some time on the water jet to water jet out some of the parts on our shooter. But a lot of it, yeah, essentially every bit of time leading up to competition, which is what we're in right now, we're writing out hectic grant requests and sponsorship requests to different companies and feeling around. We're lucky enough that Google gives enough to cover registration fees to both us and our sister school at Mountain View. They give it to the district and it gets proportioned up. But that just covers registration, which is about $5K per competition. Yeah, they're working on reducing that, but we'll see.
Mountain View is 971.
Yeah, Mountain View is 971. They're a very good team.
It seems that you're expected to be pretty proficient in a lot of things.
Yeah, so
even knowing 3D CAD design, knowing how to use a water jet, knowing how to use OpenCV.
Yeah, so there's a network of mentors that you can contact, and you always have mentors coming to your team to help you out. In our case, at Los Altos, we're really proud in the fact that we have about 2 mentors that we really go to if we're super desperate, whereas everything else is student taught, student designed. Right now, we're fortunate enough to have a 7th period class at the high school, which we're using to teach new members of the team how to do all of that. They're working on essentially a mini FRC competition that we've designed to shoot ping pong balls into targets. We basically scaled down this game and had them build little robots to compete in. They're going through and machining them, coding them, all that. But yeah, a lot of it is done, passed down from year to year, as well as there are extensive web resources based around the community of other teams. If you are a team that needs more help in that regard, you can, so part of that 5K per competition registration fee gives you a kit of parts. Typically, it's just the game pieces, in this case, dodgeballs, which for some reason cost about $60 each. They've never had good luck with that. But you can either opt in or opt out to getting a drivetrain. So Andy Mark, which is a big, almost FRC-specific provider of parts and resources, provides these. They do these Andy Mark drivetrains, which are 6-wheel, very easy to bolt things onto. Which you see being used by a lot of rookie teams as they're still trying to work up how you get all of these components into one functioning robot. But typically we opt out of it just because we can use we get a voucher for Andy Mark instead, and we can use it on parts that we're going to need more than a drivetrain. And a lot of that's just because we've been doing these 6-wheel drivetrains for years, and so it's passed down very cleanly from generation to generation.
You guys are Team 114. I think they're in the 3,000s now, aren't they?
They're actually up to the 6,000s.
Wow.
Yeah. That being said, I don't know how many of those are still active. I'd estimate about 3/4 of them are still active. Probably a little bit less.
Your first year is probably like.
We were
87.
the second year of first we joined.
Okay, so you're 4.
Yeah, if they assigned them based off of year that you joined, we'd have a lower number. But they started originally giving random numbers to each team, and then one year decided, okay, we're just going to distribute them mostly based off year. Yeah.
So on the shooter, is it constant velocity, and therefore you're dealing with the angle?
So we experimented with both the constant velocity on the. So you can see there are little magnetic encoders on there. There's the leak. Yeah, so we experimented with both the constant speed and the angle adjustment, as well as doing a combination of both. We found that our shooter was really, really overpowered for what we needed to do. So we were able to get away with only having about 2 different angles we needed to play with and just give it full power to the wheels and angular velocity. And we were able to make it in, like I said, 9 out of 10 times.
But the actual thing that's doing the projection of the ball, you've settled on a constant velocity for that, and then... Okay.
And then we're playing with the angle of the shooter.
Now, on the angle, when you lock it down before the shoot.
So
in other words, I could envision the thing just jerking.
Yeah. So we don't have a mechanical lock.
Or maybe it's heavily geared.
Yeah, it's heavily geared, and we have a very, very well-tuned PID system on it.
Oh, okay.
Yeah.
So if it's really overpowered, you just sort of make your own hole in that time.
I wish. I feel like we might get disqualified for that. David, I think you have some more videos, right?
Yeah, I do.
We need to move along.
Oh, sure thing. Yeah, I think
Thank
we've
you very
taken
much.
more than
Team
that.
114, we're the Fighting Eagles.
Eagle Strike, Los Altos High School.
Strike Eagles.
Los Altos High School, yeah.
Los Altos High School. Look forward. You guys keep coming to the club meetings every month. Last
Well,
Wednesday every month.
hopefully we'll bring another one once we get it built this year.
Okay. These two are bot vacs. Unlike Loco-Mo, which has a computer on top, this is Marvin rather. Marvin has the Raspberry Pi with the the HBRC SIG. We're going to be training on bot vac, ROS, specifically on the Raspberry Pi. And then this guy bolted a, this is Marvin, I bolted a TurtleBot chassis to our latest D3 bot vac here, and I'll have the Raspberry Pi in it. And once I get the ultrasonics straightened out in navigation, that shall be a glorious day. Nathan Monson, tell us more about Cosmo. But before that, are there any more robots?
Okay. That concludes the organized, I put that in quotes, portion of the meeting. And people who have to take their children home to get them into bed, now's a good time. There's a brown box over there, and if you don't have your red, white, and blue badge, you just have a regular badge, and you want us to keep it for the next time, just throw them in there, okay? Otherwise, you can take them home and, bring them back. If you decide to come back. We'll be meeting here on the 30th. Okay, thank you very much. And I will kick everybody out at 10, and the rest of us just talk robotics for the next hour or so. And then we go outside, and those who are really feel like battling the cold can talk some more until the Google guards come along and kick them up again. Okay, thank you very much.